a ride. And yeah, I will show you just briefly various things I have done in the past and some things I am still doing right now. And I hope you'll find them interesting and we get to collaborate, at sometimes in the future. Okay. I don't know the format, how I should introduce myself or to do it on the fly while doing the presentation.
Yeah, you could just do it on the fly while you're presenting.
Okay. I tried sharing my screen earlier, so tell me if you see my screen. Do you see my screen?
Yes, I see your screen. I think everyone else also sees your screen.
Okay. Yeah, thank you once more. My name is Chinonso Onah, and yeah, I started my journey from studying elementary particle theory and some background in mathematical physics and ended up in quantum algorithm for optimization problems. However, my interest and expertise really is not restricted to combinatorial optimization problem, but quantum computing applications in general, real life applications, not what theories will call applications, because what theories will call applications are just hard but not necessarily useful. If you approach real life applications of computational paradigms, not just quantum computing, you get into really big problems. And sometimes you don't know how to proceed. Okay. Let's start from the beginning. I took a very long walk to quantum algorithms, and you will see in a moment why it is quite long. This is the short form. I started from elementary particles, and right now I'm working on quantum algorithms. I did my BSc at the University of Nigeria, and I did my bachelor thesis on discovery of the Higgs boson and the implications for theoretical physics. And this was my first exploration into field theories and their manifestation as particles, which was really very interesting. And when I did my bachelor thesis in 2015, it was just a couple of years after the discovery of the Higgs boson at CERN, and it was the most important topic in theoretical physics at that time. Even till now, it is still the most troubling theoretical problem in physics, the discovery of the Higgs boson, because not only was it discovered, but it doesn't fit the theory at all, right? The properties of it does not fit the theory, and there is no explanation for this. So I found this very, very interesting and challenging, and I wanted to continue doing this in my master's program. Fortunately, I got some scholarship to go to South Korea. I did my MSc in Seoul National University, and I wrote my master thesis on non-minimal composite Higgs mechanism. So this is a different approach to theoretical physics, where you build some model, you have some ad hoc intuition from phenomenology, and you try to build a model that reproduces what you see in experiments. And the problem with this approach is that it's based on group theory, because in particle physics, the particles are field excitations. So these are represented by group adjoints. Okay, so what happens is that the particles always appear when some fundamental symmetries are broken. Now, so what theorists did here was to enlarge the symmetry groups that are used to represent the fields, so that when that symmetry is broken, right, the particles that appear will have properties that agree with the experiment. The problem with this is that if you do this, you would reproduce the Higgs particle, right? But then other particles are present, and if you don't observe this particle, is either your theory is wrong or the energy scale is very, very high that you can't see these particles. And with this doesn't give any good theoretical guarantee, because you can't always assume that the energy scale is always higher than you can observe, because then no theory can be wrong and you can't validate these theories. So I was not satisfied with this. I still wanted to get deeply into mathematical physics and study theoretical physics, field theory from a more fundamental point of view. That I joined another master's program at Ludwig Maximilian University in Munich. So I wanted to get into mathematical and theoretical physics, and I did get into that. However, here I tell you my first story, because when I joined the second master's program in mathematical physics, I now encountered quantum computing. So in my first semester, I immediately joined the research group, and we are working on topological field theories and exotic particles. Now, topological field theory gives rise to certain other exotic particles like solitons, like domain walls, like magnetic monopoles, even black holes can appear there. However, apart from black hole, the other particles are not easily observable. However, experiment has not ruled them out. And in these topological field frameworks, you can also derive neutrinos and some other observable phenomena. So this is not totally ruled out. The only problem was that in my first semester then, I decided to look for some student jobs to keep body and soul together and at least have something to eat while I study mathematical physics. And I got a job as a student assistant in Quantum Application Research Lab. This is a different chair in computer science, not in physics, and they were involved in quantum computing. Right. So so I knew about quantum information theory. So it was so I needed some crash course on quantum computing to start doing quantum computing. So I basically taught myself quantum optimization by studying the QoA algorithm and looking at how it was implemented on IBM. And to convince them to hire me for my experience, I developed a QoA mascot solver for random graphs. So what did that mean? If you give it any random graph, it will translate that graph to some Ising Hamiltonian and solve the mascot. So for this graph here, this blue is the mascot. If you look at this graph, there is no other cut you can make on this graph that will cut as many edges as this problem, as you see on this image, right? So this gives you the maximum cut, and you can implement a QoA algorithm on this problem and get an approximate solution. If the problem is small enough, or if you choose your parameters well enough, you can get an exact solution. So I guess many of you here know about this QoA algorithm. And this is quantum approximate optimization algorithm. So basically, it is an approach to quantum optimization. I should say more about this in a moment. So, so what I didn't say here is that just 3 months after I was starting working here as a student assistant, I also got an opportunity to join Intel Labs. So Intel has a research lab. They have research in basically all computing. So this is something that people don't know very much. Intel, Microsoft, Google. I mean, right now, most people know that they do quantum computing, but the fact is that they have teams researching all forms of computation that are remotely possible. Optical computing, neuromorphic computing, Ising machine computing, of course, quantum computing. Okay, so, but I don't mention Intel Lab in this slide because it was about neuromorphic computing, and I shouldn't bore you with neuromorphic computing. Okay, so since I started working on quantum algorithms, I didn't want to do my thesis on topological field theory anymore. I actually wanted to do my thesis on quantum simulation of black holes. So there is a phenomenon in black holes which is called memory burden. So this is a situation whereby there's too much information, because black holes are known to saturate information upper bound, so they contain maximal information. And what happens is that once this maximal information is reached, black hole begins to evaporate. So that what is said is that the memory burden of the black hole forces it to evaporate, right? So this is well studied in topological field theory literature, and I wanted to put this to simulate this from quantum computing, but unfortunately, I had a problem with my supervisor, and he didn't want to supervise me anymore, and I had to find another supervisor, right? So this was a supervisor I already found when I was in Korea, but I was now in Germany for a few months and well integrated into quantum computing, and I had to find another supervisor, and I went all the way and all in into quantum computing. And so I went to Fraunhofer Institute for Production Technology, and I got a thesis position in quantum computing. And the thesis was actually on identifying high value applications of quantum computing. This is actually not trivial because no one knows what the high value applications are. But first of all, I was made to read hundreds of papers to identify constituent problem characteristics for those industry problems that have been solved on quantum computing. And in my master's thesis, you will see many pages like this that try to summarize problem characteristics from hundreds of pages of literature. I ended up deriving about 30 problem characteristics that the problem will have to be solved to quantum computing, depending on problem structure, quantum properties, data structure, solution structure, etc. This is not entirely interesting from a theoretical point of view. This is mainly of interest to industry players who have no background in quantum computing. So for a theorist, you analyze a problem based on complexity theory. How does it scale with time or with memory? And what you see here, is if you try to solve a problem using only classical resources, the problem will, the runtime or memory consumption will grow exponentially with time, right? And if you solve it on quantum computer, then the resource consumption of quantum computer is not expected to grow exponentially. You should have this kind of linear or polynomial growth, right? But that is if you have a full quantum implementation. What I did in my thesis was to show that if you, however, even on the currently available quantum computers, if you integrate quantum and classical approach to the solution, to the problem, you can find a solution where the exponential growth is suppressed. So you see, this red here still grows exponentially, but is much, much more suppressed compared to this one. So imagine you could always solve more than double the problem with this hybrid classical approach than you could solve with purely classical. And this doesn't mean that you do any quantum intrigue. No, this was a simple demonstration where you have a mixed integer programming problem where you generate constraints, and on a sub-problem you solve it using QUBO. So usually on a classical computer, you separate these two approaches. You have the constraints that generate some problem. It is called column generation, and then you solve the problem for each column. And just by outsourcing the sub-problems generated to a quantum computer, it was already possible to scale up the problem sizes, right? So in this way, you can already see some usefulness of quantum computing. Some people could argue, oh no, if I outsource the sub problems to a GPU, I would also be able to solve the problem. Yes, but if this classical computer is slowed down by this exponential growth, it would happen to a GPU or to anything. And however, quantum computers will also become more and more powerful. So this was the main theory I developed in my master's thesis, and I developed this framework using nonlinear regression. So I don't want to bore you with more details, but you can ask me at the end. And this is just what I did was to, if I take any problem or any behavior, be it memory or be it runtime, I can find the exponential growth of this computational resource with problem size by fitting it to this model. And if I introduce a hybrid quantum classical solution, I fit it to the same model. And always there is a huge separation between the classical and the hybrid classical approach. So that is about the second master's thesis. Okay, so something else I also did was to work at a company called Parity Quantum Computing, which is a quantum architecture company. So I started working increasingly more about quantum architecture, where I focus on circuit compilation for different problems. So what is the problem? If I give you a quantum circuit, you have to represent that circuit as some intermediate representation, maybe open chasm or QH or some other. There is also QDL nowadays. There are many, but open chasm is the main intermediate representation language known. Then you translate this circuit into your internal data structure. So all these quantum computing providers or any compiler at all will have its own internal data structure that it uses to represent the circuit you have given it. Then it has to manipulate the circuit such that it remains faithful to the initial input and gives you the output as a quantum instruction with as few number of gates as possible and as much parallelization as possible. So this is also trying to beat the quantum coherence time limit that any quantum algorithm or any quantum circuit needs to meet. Otherwise, you don't have quantum computation. So there is also something else where you have modular quantum computing. So imagine that your quantum computer is spread out. So you have a quantum computer that is built by combining different quantum computers, right? So maybe a single quantum computer has 10 qubits, the other one has 12 qubits, the other one has 20 qubits, or maybe for simplicity, all of them have 10 qubits. And you want to compile a circuit that runs over 50 qubits to all of them. What you do is that you take the quantum circuit, right, and then reduce it into a set of circuits and instruction and shuttling instructions where some qubits must necessarily move from some quantum computing units to another quantum computing unit to execute instructions. So imagine you have 3 interconnected units that act as one quantum computer. But then you want to do a gate that has 1 qubit from unit 1 and another qubit from unit 3. So you have to physically move the qubits from unit 3 to 1 to execute that gate. So this means that you have to translate your circuit into a shuttling instruction. And because moving a physical qubit is costly, it takes time and it's prone to errors. You want to have few of them, very, very few of them, as few as possible. And this, you can do this by brute force, basically trying all the possible combinations of qubit movements to find which one has the smallest number of movements. That's what we call brute force. Or you can formulate this as an optimization problem and find the minimal number of shuttling that gives you the same circuits you want to implement. This led to using simulated annealing or greedy algorithms or exact algorithms to solve this problem. So at the end of the day, you see that for the circuit compilation, we have a host of optimization problems that have nothing to do with quantum computing. So after doing this for like 9 months, I felt like I needed to find my expertise elsewhere, right? Because this is a very hard software engineering problem, and there's also a hard optimization problem. It's interesting because you would need this to make quantum computing scale to the next level. So I then changed my focus into quantum applications. What you will see here is that the task of optimizing this circuit here, or the task of optimizing this shuttling instruction has nothing to do. I mean, if you understand the structure of the circuits that is put in here, you can still utilize this structure when planning these instructions, right? But my interest is in what is fed into this algorithm. So translating the physical problems into quantum algorithms. So this has a lot of problems, right? Then let me take a detour and show you the roadmap of some of major quantum computing players. So this is what we are going to see in the future, and how does that take us to quantum utility? So, for example, if you see here, superconducting qubits, IBM plans to have like 100,000 physical qubits in the next 5 years, basically. And right now, what IBM is targeting is to be able to do 100 gate cycles on 100 qubits. So that is their 100 by 100. That is their 100 by 100 challenge, right? I'll have more to say about that in a few slides. And then here you see Google is also pushing superconducting qubits and wants to get 1 million physical qubits by the end of this decade, by 2030. Right? But what can we really do with these physical qubits? They also plan to get 1,000 logical qubits by 2030. So this will be a lot, but how much problems can it solve still? We'll still say more about this. It is not clear how much qubits IonQ tries to deliver, but they are delivering what they call algorithmic qubits, which means essentially where you use all the qubits they give you in computations, right? But there is a challenge to this also. You will see there is quantum computing has a utility problem, which I will get to again very soon. Quantum also has a more modest ambition, although I think they have already exceeded these numbers here, but they plan to get 24 algorithmic qubits by 2030. I think they already have more than this, which is a very welcome development. Pascal also plan to get 1,000 qubits by this year. However, they have already reached this, and there was a recent demonstration of 6,000 qubits from neutral atoms, but I think it's not from Pascal. D-Wave, of course, has 5,000 qubits, but that is a different ballgame entirely. Okay, so one thing is, how do we use these quantum resources actually, right? So what can we do with them? Now, if you have a quantum circuit, then it consists of the qubits and then the cycle of gates you implement on the circuit to solve a certain problem. And even considering there is noise in the circuit, you must have the probability of error must be much less than the breadth times depth of your algorithm to have a meaningful result at the end of your computation. Now, this is not talking about quantum error correction. If you have quantum error correction, this is the probability of error is going to be 0 actually, and this is satisfied. But if the circuit is not error corrected, right, then the non-trivial probability of error still needs to be much less than the inverse of the breadth and depth of your algorithm. So think of the depth of an algorithm as the number of gate sequences you have to implement to solve a problem. And think of breadth of an algorithm as the number of qubits involved in your problem. And this relaxed requirement is actually responsible for all the problems we have in quantum computation, because if you have a shallow circuit with 1,000 qubits, if you have only 10 gate cycles, you are required to have fidelity of at least 99.99% in the quantum hardware to be able to do this these shallow circuits. But I can assure you that a shallow circuit of 1,000 qubits and 10 gate cycles doesn't solve any interesting problem, and it may be simulable by a quantum computer. So this is not a quantum computing interesting application. So the quantum computing has this fidelity problem. Even ion traps that have the highest gates, the highest gate fidelities do not reach this limit. Okay. Then there is also the problem of identifying quantum resources needed to reach quantum utility. Now, the hype following quantum supremacy and quantum advantage has made it uninteresting. So because people are always talking about quantum utility, about quantum advantage and quantum supremacy, so this motivated the invention of artificial problems that are just hard to solve but correspond to nothing, at least nothing interesting. So the main interest now, and also as someone who work in industries, I also know that the interest is not whether there is quantum supremacy or not. The question is there a useful problem that we can solve with quantum computer, but we cannot solve with classical computer, or where it is even more useful or more cost efficient to solve on a quantum computer than on a classical computer. So if you can make any case at all, whether it's energy efficiency, cost efficiency, or time efficiency, some useful problem. However, the main problem is, so what application will you use quantum computers for? So this is actually a big problem, and I think it is the most important problem for quantum computing right now. I may be biased since that is what I'm working on, but think about this. So there is an open competition right now, and both BMW and Airbus and Amazon Web Services will give $30,000 to several winners who develop quantum solutions to their challenge, to a particular challenge that they pose to the community. And just a few months after that, Google announced their X prize, which is nothing but $5 million to, I think, 5 teams who come up with a useful quantum computing application. So the bottom line is that even the guys who develop quantum computing, they are developing the ability. And that's exactly what I saw when I was working as a quantum software engineer, right? We were developing abilities, right, to make these quantum computers useful. But useful for what? So this is not known, and because you actually have to find a problem that quantum computers struggle to solve. So let me give you an example from a vehicle routing problem. So since I'm currently working on mobility problems mostly. So in a vehicle routing problem, each vehicle has some capacity, and it must take a tour from the depot, serve some customers' demands, and come back, right? And if you formulate this problem with one-hot encoding, you could end up where the number of qubits scales as the number of customer locations, which is n, the size of the fleet, that's the number of vehicles in the fleet, and times q, which is the constraints, the capacity constraints on each vehicle, and you have the number of qubits growing like this. Then you can think of a scenario too, where you actually use binary encoding of the problem, and you can save some costs by binary encoding. So which essentially means taking advantage of quantum computing, because you cannot do binary encoding with classical computer. So if you take advantage of the binary encoding that quantum computing allows you, then you can now suppress this growth by requiring the number of qubits to grow as k dot q times log n. Log here means log into base 2, right? So from what I've seen, the number of qubits, this basically reduces the number of qubits by half. So there's another approach to solve capacitive vehicle routing problem. Classical algorithms usually, especially heuristic algorithms, usually solve problems by breaking it down they try to break down the problem into sub-problems and then try to combine the solution. So this is a well-developed algorithmic procedure in classical computing and should actually come into quantum computing. It's also part of what I'm working on right now. So if you decompose that, each sub-problem, the number of qubits will grow as n squared if you use one-hot encoding, or it will grow as n log n if you use binary encoding. So the question is, if you look at this problem here, the number of customer location in each of these problem instances, the instance here just means a name, the name of a particular vehicle routing problem that is out there. Anybody can look at it and solve it. I picked these problems, number one, because they are hard. Number two, they are not solved to optimality. So if you use a quantum computer and solve them to optimality, that will be a clear, useful quantum advantage, because this is a real life problem and the optimal solution is not known. So now what I mean by optimality gap is if the classical computer has a gap, let's say the classical solution is 20% away from the optimal, and the quantum solution is 5% away from optimal, then it really makes sense to use quantum computers. But since this problem is NP hard, you don't know the optimal solution. So you don't even know how good your solution is. So this is actually hard. So you don't know how far away you are from the optimal solution. So if you get a solution that is slightly better than the classical solution, you don't know how much progress you're making. And this will not motivate people to buy your solution. So the big question, what's good is quantum computers remains wide open, right? So now I mentioned here that how you encode your problem matters. If you use one-hot encoding or binary encoding or whatever, there are many. I put ETC here because there are many ways to encode a problem. There is something called the domain-wide encoding also. But it turns out that binary encoding is the most efficient. So as you could see earlier, it would actually have the problem, the number of qubits required for a problem. And then it will really make a huge difference. And the only cost you pay is that your gate depth is longer. So, but it's longer by just a single order of magnitude. Okay. So if I have a problem, I have to choose some way to encode this problem. And then I have to choose an algorithm. I have to choose a hardware, and then I get a solution. So navigating this path is always not straightforward. So this is also a problem for quantum computing, because if I find a different problem, I find a way to encode it, then I pick an algorithm, I may find out that the algorithm depth is too much, and then I must find the other one. I must choose another encoding, which may make the problem infeasible for quantum computing. All right, so these are some of the problems I'm taking on right now. And like I said, in the industry, the most important problem right now is about utility. So you wouldn't take the pain of implementing a quantum solution if a classical solution is good enough. So what are those real problems that make the pain worthwhile? That is the open question for the whole field, and that is what I'm focusing on right now. Where I'm working at the Volkswagen Group Innovation, and somehow this research will also lead to a PhD thesis, as I'm also enrolled in the PhD program at RWTH Aachen University. This is the end of my presentation. I hope to be able to answer some of the questions you have. Thank you.
Thank you so much, Chinonso, for the very interesting presentation. And actually, your journey alone is really inspiring. I think I would have some questions, but maybe I should begin by asking a more kind of general non-technical questions, because I guess also some people in the audience are also coming from non-technical background. So your journey is really of a technical approach, I would say. So perhaps how will you kind of advise someone planning to get into quantum computing? You mentioned that you taught yourself a lot of the basics initially. So is there a way that someone, let's say obviously with a science background, is thinking about hopping into quantum, the world of quantum? Is there any piece of advice you have for them on how to get started?
Yes, and even though I had a bit of technical background in physics and a little bit of mathematics, the easiest point of entry is the same. Find some easy solutions and reproduce them. So if you go to your nearest search engine and type in quantum optimization tutorials, you are going to find at least three Medium articles that apply quantum optimization. You will find at least three YouTube videos that did quantum optimization. You will find some Jupyter notebooks that use Qiskit or Penny Lane or Zapata's backend to solve some quantum optimization. So find any of these. Maybe do this in parallel. So listen to the YouTube video and just try to get a feel for it. Try to actually run the notebooks and then read through the technical descriptions. If you come from physics background, then pay attention to the quantum mechanics, the state space, the Hamiltonian, and all that. If you come from non-physics background, just pay attention to the linear algebra because these are basically linear algebra operations and with a bit of operator theory. So just look at the tutorials and only tutorials until you can reproduce some of them, even by copying the tutorial basically. And to get into the field, what I discovered is that it is best for you to get in from where you are right now. So don't wait for any particular expertise. So for example, I've been advertising in Nigeria community here in Germany for if you want to do any internship or any thesis position in quantum computing, regardless of what your background is, just get in touch. You might be able to find something from my current company, right? So the same with PhD. So I have a colleague in our company who is also doing PhD, and he did his bachelor's in physics, his master's in mathematics. In his master's, he just worked on graph neural network for material simulation. He doesn't know how to translate a unitary gate into a quantum. He doesn't know how to translate a unitary operator into a quantum gate. But he was hired at the end of the day because he was able to prove some interest. So if you have some interest, get into the field from right where you are. There is nothing to wait for.
Oh, great answer. So let me allow the general audience to ask a question. So you could use the chat or feel free to unmute yourself and go for it.
Yeah, hello, can you hear me?
Yes, I can hear you.
Yeah, so thank you so much, Nonso, for that wonderful presentation. And yeah, thank you, Obina, for raising up that question. Actually, so I just want to ask something based on what you just said last, right, about the community in Germany, the opportunities you. So this opportunity is only available for those in Germany. It's only available for the people.
Yeah, it is. It is since my company is based in Germany and I basically need to talk to my direct supervisor about this, right? So it would be available to people outside Germany only if there is an official recruitment process, and in the recruitment process, you would see if it's a recruitment that supports your visa application from overseas, right?
Okay.
So, but if you're already a student in Germany, you're already in Germany, then it's not difficult at all to move from your current city to one of our offices and work from there. And there is also something I can mention about getting into the field. So if you I talked about looking up some tutorials, right? If you also Google quantum optimization, you will also find some tutorials published as lecture notes or published as journal or as preprints, but are not peer reviewed. Some of them are even peer reviewed, right? So the field is so young and the demand is so high that whatever you can contribute to the quantum computing community can actually facilitate your entry into the community. So the community is looking for any form of, would I say, commitment, or maybe it's just any form of effort that indicates that this guy is, or this girl is really interested in quantum computing and has some abilities, even if it's not directly related to quantum computing.
Oh, thank you so much. Thank you for that.
Yeah, thanks, Austin, for the question. So, any other questions? So, someone asked if they can have your LinkedIn contacts. I think Horacio, I'm not sure of the pronunciation.
Yeah. So if you can have, so you can see my name, you can just put my name in LinkedIn and you clearly send me a connection request and I will be happy to connect. And if you have any, if you want to have any discussion about quantum computing, certainly about applications of quantum computing to actual problems, just send me a message and I'm happy to discuss.
Okay, so I think we have time for some more questions about two. So let's see if anyone also have a question. Maybe why some people are making up their mind or typing, because I guess some would prefer to use the chat. Maybe I'll go for a second question. So my question would be based on the fact that, I mean, there's a lot of hype in quantum, and I want to be optimistic, obviously, that I mean there's a lot of problems out there that quantum alone can solve. Although there, as you mentioned, also there are some hybrid problems that perhaps for the near term would just require the fusion of both quantum and classical algorithms. And so that being said, I'm thinking about, let's say, for someone, just as you motivated us, that we could just get into the field right now. What's an example of hot topics in quantum to kind of get into? I know you're working on optimization, perhaps you'll be biased on it, but are there other hot topics in quantum?
Yeah, the most, I think optimization is not even the most promising application of quantum computing. The most promising application would be simulation, so material simulation. I guess most people here are physicists, so if so for any given material, the system is actually a quantum system. So a highly correlated quantum system, highly complex. This means that the Hilbert space is really huge, and this leads to memory explosion on classical devices, so that always the realistic simulation is hard. So this is why many quantum advantage applications have always been in simulating some Hamiltonians. So simulation, if you are focused on where quantum computing will establish the earliest superiority or earliest usefulness, I think it will be quantum simulation. The only combinatorial optimization is important because it applies to a huge family of problems. And if you do study the field in any detail, you will first of all, you will immediately learn about NP completeness. And this is a phenomenon where several different seemingly unrelated problems are actually identical or can reduce to each other, quite efficiently, so that if you solve one problem, you have solved all the other ones. right? So, and these problems appear everywhere: hospital scheduling, bus scheduling, vehicle routing, timetable scheduling, machine scheduling in industry, in finance, in drug delivery, etc. These problems are everywhere. So that, and they're also hard to solve. So that for realistic problems, they are always approximated. So if a quantum computer can solve them exactly beautiful, if it can approximate them better, faster, or more energy efficient, because computation also takes energy, right? So there are many ways to approach these problems. But what I think is that as long as the problems remain open, there will still be need to explore different ways to solve them, which is why there are many computing paradigms being explored right now, even beyond quantum.
All right. Thanks so much. See, we actually have a huge library repository to choose from. Yeah. So let's see if we have any other question. Okay, I see that perhaps all right, is someone trying to go ahead, please?
I don't have a question, and I'm living in Augsburg, not so far away from Munich. And I have a physics background, and after that I complete my master in material science. Always I'm working since almost 4 years in automobile industry. That means I'm just using 0% from what I learned at the university. And I'm now really looking for something to start some, I don't know, cybersecurity or something new, but related almost to physics and now I'm still checking which field will be easier or which field is better. But I'll contact you already in LinkedIn. I sent you a request already in LinkedIn. I think we can discuss that about all the stuff that you are doing, directly. You have time, of course.
Okay.
Thank you
Yeah,
for the
thank you very
presentation.
much.
Okay.
Yeah, I will get back to you on that. And of course, there are many open problems. So especially also in automotive industry. And if you also have background in the automotive industry, that is actually extremely useful. It is more useful than you realize. I didn't mention it here in the slides, but one of the conclusions I have arrived at as the bottleneck to quantum computing is domain expertise. So, like I said, the main open problem is what is quantum computer used for? And this has to be domain by domain. So in automobile, the question is, what are the problems in this domain where quantum computer is advantageous? And it is not possible for an outsider to discover this problem. It is someone who has domain knowledge in applications of in automobile industry that will say, oh, this problem is a problem in my domain and it is hard classical computer. Then someone who knows quantum computer will be able to say, oh, let me see if this has an efficient quantum solution. And that's how that is one of the ways where breakthroughs can be achieved. So if you have both the domain knowledge and the quantum computing knowledge, then you are in a very good position to be able to bridge this gap. Or somebody who doesn't know anything might say, oh, this is an automobile problem, and here is an efficient solution for it. So, for example, somebody might, it hasn't happened, but what if someone says, oh, this is a 1,000 node traveling salesman problem. It is a useful problem in logistics of domain, in logistics or automobile. Here is it. But no, classical TSP solvers can solve 1,000 node problems in seconds to optimality.
Okay.
Yeah, so even though it is an interesting from a quantum computing point of view, but it's not yet that exciting application where quantum computer cannot manage it, and we are hoping that quantum computing will be a breakthrough. So it's interesting, but it's not that of a computing breakthrough.
Okay, thank you.
All right, thank you, everyone. I think we are actually on time, and we would be drawing the curtain today. And sure, if you have any questions, I think Chinonso have said you can reach him on LinkedIn, which just by searching his name, you'll be able to get him on LinkedIn, and I think he's fine to answer any questions you have. All right, and we'll have a YouTube channel, so I would upload this video there, and be able to share it to your friends, and keep in touch also for our next seminar, also coming up soon. You get this invitation via email, because I think if you register now, you would be part of our mailing list. All right, so thank you, and see you next time. Thanks again also for your time. We really appreciate your coming here.
Okay, bye guys.
Thank you. Bye.
Bye, guys. Thank you.